Hello and welcome back to your Organic Chemistry 1 lecture. We are moving forward this semester. We're rounding the curve here. We're almost at the end. We're entering exam 4 material now by starting to look at chapter 8 or chapter 9. So it's chapter 8 in the third edition book, chapter 9 in the second edition book. Either edition will work just fine. But yeah, what we're going to talk about is we're going to talk about addition reactions. So in the last two chapters, or the last chapter, we covered substitution and elimination reactions. The next big class of reactions that we need to talk about this semester, and it's really the last class of reactions that we'll talk about. We're also going to have additions to alkynes later, but we'll get to that next chapter. This is the addition reaction. And the addition, you can think of it as basically the opposite of an elimination. So in an elimination reaction, you have two carbons that, one carbon has a halogen bonded to it, the other one has a proton bonded to it. The proton is deprotonated, the halogen leaves as a halide, and you end up with a pi bond in the middle. So it kind of is like you have X and Y bonded to two neighboring carbons, and you end up over here with a pi bond. Addition is the opposite. This is where we're going to take a pi bond and we're going to add two atoms to it. So we'll just call these generically X and Y for now. As we're about to see, we're going to go through just the list very briefly here, the different types of addition reactions we can see. Those will determine what atoms X and Y actually get added to those there. So you just note kind of that the carbon-carbon pi bond is going to be converted into two new sigma bonds. So we break the carbon-carbon pi bond, we form two new carbon sigma bonds, carbon X and carbon Y. So just these are the mechanisms that we're going to learn this semester. And so we'll just kind of give an idea here. So hydrohalogenation is the addition of a hydrogen and a halogen, just exactly like it sounds like. So you've got, a hydrogen being added to one carbon, and then, some halogen X, so chlorine, bromine, or iodine. That's what we call hydrohalogenation. Next up, we have hydration. So that's where you think of it like adding a water molecule. You're going to add one proton to one side. So one hydrogen atom gets added to one carbon, and then an OH group gets added to the next. So you're basically taking an alkene and you're forming an alcohol. Next up, you have straight hydrogenation. This is just where you split a hydrogen molecule, H2 gas, and you add two hydrogen atoms to one to each of the carbons that is in the pi bond. Next up, you have halogenation, or you can even think of it as dihalogenation compared to the hydrohalogenation. This is where you actually add two halogens, one to each side. And this only works with chlorine or bromine. So yeah, halogenation here just gives you the, both of these are going to be bonded to the same type of halogen, whether it's chlorine or bromine. And we'll talk about that next, later on this chapter. Next up, we have halohydrin, which is sort of like a mixture of hydration and halogenation. So you get an OH group on one of the carbons and then a halogen on the other of the carbons. And we'll talk about how you can do that in section 8.9. And then finally, we have dihydroxylation. And there's a couple different mechanisms, a couple different ways that you can do this. But dihydroxylation just installs, two hydroxyl groups or two OH groups on the neighboring alkene carbons. So I hope that makes sense. It's basically you're taking a carbon-carbon pi bond, you break that, you form two new sigma bonds, and then the type of reaction obviously is going to depend on what reactants you use to do that. Okay, so when we do these addition reactions, most of the time, the pi bond is going to act as an electron pair donor. So we talked about this very briefly in a previous chapter when we mentioned that a pi bond can function as a nucleophile, because a pi bond, is a collection of, bonding electrons. It's an area of high electron density. So that means it can function as a nucleophile. And sure enough, that's what we're going to be doing a lot this semester, or, for this chapter and the next chapter especially. So what we have is basically the pi bond acts as a nucleophile. It does a nucleophilic attack on a proton or another electrophile. One of the carbons in the pi bond is going to form a sigma bond to either the proton or to the electrophile, whatever that happens to be. And then the other carbon that's left over, that's going to form a carbocation. So this is how you're going to write these arrows, basically. It's a nucleophilic attack, but it's going to start from a pi bond. And again, we mentioned that that was possible before. Now we're actually going to see it in action a lot. Okay, so alkenes show up all over the place, both in biology and in industry. So these are some alkenes that you're familiar with from before. Allicin is what gives you the smell of garlic, whether you like that or not. This is allicin here. Geraniol is a perfume, and it smells like roses, basically. So I guess it's actually isolated from roses, so that makes sense. Geraniol, you can kind of hear geranium. It's like flowery. And then alpha farnesene. This is basically responsible for the natural waxy coating that shows up on apples. So not the artificial wax that gets installed later, but this is what's responsible for the nice coating on apple skins that you like rub off on your shirt and makes it all shiny and stuff like that. And then we have limonene. So that's the responsible for the smell of oranges. Again, an alkene. This is a cyclic alkene. You can see that we've got, what looks like an isopropyl group, but actually has an alkene on it. And then within the cyclohexane ring, we actually have a cyclohexene. And then cholesterol and many steroids, have these polycyclic systems. These are, like a steroid type system. And cholesterol has a carbon-carbon double bond in one of its rings. So cholesterol is also a polycyclic alkene. Pheromones as well. This shows up. So like codling moth, aphid, and the housefly. These all have these alkene based pheromones. I'm not sure exactly why that is the case, but it is just the case that it shows up in a lot of natural products. And sure enough, these insects really like these alkenes. Okay, but then in industry, we actually kind of intersect with um, a lot of basically the what gets produced from these alkenes every day, because these alkenes serve as precursors in the chemical industry for plastics. So ethylene and propylene are two of the major products from petroleum. So yeah, so we have down here 200 billion pounds of ethylene and then 70 billion pounds of propylene. And this is ethene and propene, just the old ways of saying it there. And these are crucial for a wide variety of plastics, especially, and then other commodity chemicals that you have to use. So if we look at petroleum, we split it into ethylene. Ethylene gets made into polyethylene, and that is, probably the most common plastic that we interact with on a daily basis. So, everything from your grocery store bags to your chair to your milk jugs are going to be made from polyethylene. So it's, probably the most important plastic that there is. And then there's all these other things that you make from it. So ethanol. So even though ethanol can be, fermented and distilled, you can also produce ethanol from petroleum and from ethylene. And if you need really clean ethanol, that's what you do is you take it from ethylene. But I think it's still cheaper to just distill it for the most part, unless you really need something. You can also make acetic acid the same way. And then another one down here, this is kind of a longer route. You go to ethylene dichloride, vinyl chloride, and then polyvinyl chloride or PVC. You probably have heard of that, PVC piping. That's another extremely important type of plastic, basically. Ethylene glycol, that's another product. So you go through ethylene oxide and then ethylene glycol. It's another crucial product that's frequently used as an antifreeze chemical. So like some way that you can keep your car, it doesn't freeze, even though it's a coolant basically in your car's engine. If you use water and you live somewhere that it actually gets cold, then that could freeze up. So we use ethylene glycol instead, or propylene glycol as well. So propylene as well, crucial for plastics, especially polypropylene. So polypropylene, again, it's probably the second most abundant plastic that you run into. Those chairs that we use at class, if you have like one of those like purely plastic chairs, that is probably made of polypropylene. You can also make, again, isopropyl alcohol and acetone from that. If you need, extremely pure acetone, then you're going to make it from polypropylene, and it becomes one of the most important solvents that we have. Propylene glycol as well can be used as an antifreeze chemical, and then cumene. I have forgotten what cumene does, but you can look it up. It is something that's important, and I'm sure we'll come back to it later. Okay. So, right. So how does addition relate to elimination? We mentioned before that it's kind of the opposite, the reverse reaction of elimination. And sure enough, like if you just draw it out, it seems pretty clear. Like you take your alkene, you add HX, that's your addition reaction, okay? And then you get, one of the carbons bonded to H, the other carbon's bonded to X. Well, the reverse is just an elimination. You eliminate X, you deprotonate the proton, and you form your alkene like there. So the way that you can make so that's a good thing because we notice, oh, okay, it's kind of the reverse of the reaction we studied before, but it's also a bad thing, right? Because in organic chemistry, one of our goals is we want to be able to synthesize and use a particular route. And if we have a bunch of reversible reactions, well, then we're not really getting to a final product like what we want to get to. So we have to be able to manipulate it using thermodynamics in particular. So remember, the Gibbs free energy equation tells us that the delta G of a reaction is equal to the change in enthalpy plus the negative of the temperature in Kelvin times the change in entropy. So the higher the temperature is, that's going to increase the importance of this entropy term. So the higher the temperature, the more important that entropy becomes. Now, let's look at that in the context of this reaction. So addition reactions are going to be favored by enthalpy because you form two sigma bonds that are more stable than the pi bonds that you break up. So like this just kind of adds it up together. The carbon-carbon pi bond is worth 63 calories per mole, and the hydrogen-chlorine sigma bond is worth 103 kilocalories per mole. So overall, 166 kilocalories per mole. But the new bonds that you form a new carbon-hydrogen bond, that's 101 kilocalories per mole, and a new carbon-chlorine bond, that's 84 kilocalories per mole. Those are worth more. So you form these stronger bonds. You take your bonds broken minus bonds formed. You find out that the change in enthalpy for this reaction in particular is negative 19 kilocalories per mole. That's exothermic, so that's going to be favored. It's likely to be spontaneous, but we have to take into account now entropy. Now remember, the entropy, when we do this, all you do is you count up the number of moles of product versus the number of moles of reactant. Whichever side has more moles of stuff, that's the one that's going to be favored by entropy most of the time. So if we start with 2 moles of reactant and we only form 1 mole of product, that means that the addition reaction is not going to be favored by entropy. So entropy makes that harder. And remember, entropy is the temperature dominated term. So what we want to do is we want to keep that entropy contribution as low as possible. And all we have to do that is keep the temperature low. So you can do things like a lot of times these reactions just take place at freezing temperatures. So you can just use, an ice water bath, for example, 0 degrees Celsius. If that's still too hot and you have a problem, with another type of reaction, then you can move to, dry ice bath, for example. Dry ice in just a number of different solvents. We'll keep it at about negative 40 degrees Celsius. And then you could go even further to like liquid nitrogen, which would bring you down to like negative 78 degrees Celsius. So you can do those at very low temperature. And then at these low temperature, that's where we're going to get the addition reaction. And that's what we're going to find. And then on the other hand, if you want to do the elimination, you would do that at high temperature. Even just room temperature is fine usually for that. So yeah, so that brings to the final point here, just that we're going to use lower temperatures when we do these addition reactions. Okay, I think that covers our first lecture here. That does. So let me know in the comments below if you have any questions. We're going to move on into the next section where we're going to talk about a couple different mechanisms. So I'll see you soon.